Hello, thanks for clicking on this video. In this one, I'm going to talk about propositional logic with a focus on explaining the axioms at the core of propositional logic. This is the first real video of my series, Foundations of Math, in which I will be explaining the axioms of all kinds of different fields of logic and math, going up through set theory, through vector spaces and algebra, and showing how each of these fields builds upon the previous ones. And to that end, at the end of this video, I'll be showing how the axioms and the objects used in propositional logic directly form the basis for some of the objects and operations that are done in set theory. There was a previous video which serves as the introduction to this series, and you can find that on my channel in the Foundations of Math playlist. Also, between videos, I occasionally post shorts where I focus on individual topics in the previous video and try to explain them in a slightly different way, and sometimes I go into a little bit more depth. Also, you can follow me on Instagram and TikTok at Symmetry Element, where I post edited versions of the shorts which have just the most important core information, and I may eventually start posting additional content on the Instagram and TikTok that I don't put on YouTube at all. So again, thanks for joining me, and let's get started. So in propositional logic, we have propositions that we represent with letters like A, B, whatever, R, and we have implication, which we represent with an arrow. It's really just if, then. So we could have something like this. We have two propositions and an implication between them. What that says is if A, then B. And A and B are just some statement that is true or false. Like I said in the introduction video, it could be the TV is on. It could be 2 plus 2 equals 4. It could be 2 plus 2 does not equal 4, because it's just a statement that is either true or false. So propositions and implications are the foundational things. They are justified, created in the axioms of propositional logic, which we're about to get to. But that's not very interesting. So we also have these things called connectives. There are more connectives than that, but these are just a few. These connectives in particular represent and, or, and not. And we'll see where those come from too. But to give you an example, we could have a statement like A and B implies not C. So this would be saying that if A and B are true, then the negation of C is true, not C is true. So let's jump into the axioms. An interesting note is that there are other axiom systems that work and which you can use to build up set theory. But by far the most common axiom system used, just so that there's some uniformity, is called the Hilbert system. The first axiom is called implication introduction. It introduces the implication, that arrow, if then. And it's written A implies B implies A. So if A is true, then if B is true, A is still true. It's kind of like the law of identity in the three laws of logic, just simply that if A is true, then A is true. The second axiom is called transitivity or distribution of implication. And this one is a little tricky. It says if A implies that B implies C, then A implying B implies that A implies C. So think of the arrow like a gate, where the thing in front of it needs to be true in order to pass through the gate and go to the next thing. So if A is true, then we get to look in these parentheses. Okay, if B is true, then C is true. So really, both A and B have to be true in order for C to be true. So we can think about it like this. So if A implies that B implies C, then we know that this whole thing is true. And what is this whole thing? It says that if A implies B, then A implies C. And if you look at what we're doing, from the left side to the right side, we're just distributing this A. So A implies B comes here, and then A implies C comes here. Just like you would do with, say, like 2 times x plus 3. You distribute, right? So if A implies B, then A implies C. So clearly there's some connection between B and C. You could say that sort of in a way, B is like a circle that's inside C. Because then if you're in B, you know for sure that you're in C. You have to be. So if A being true means that you're in B, we already know that we're also in C, which means that being in A means you're also in C. And what is the last axiom? The third and last axiom is called contraposition, but it's also just a reformulation of the law of excluded middle. And in the Hilbert system, it is written like this. If not B implies not A, then A implies B, which just means that a statement A must either be or not be. Either a statement or its negation must be true. And from this, we can find that if you have a statement A and you want to find whether or not it implies B, then what you can do is, instead of directly proving that A implies B, you can assume that the opposite of B is true. And if that implies that the opposite of A is true, that's enough to tell you that A, in fact, does imply B. Now, with the Hilbert system, we also have one fundamental rule of inference. This is something that is used to draw conclusions from those 3 axioms. And it's called modus ponens, which is Latin for the affirming mode or affirming way. And it looks like this. So this is how it's written, using only the propositions and implications that are fundamental to propositional logic. What this notation means is that if we have that P implies Q, and we assume or we know that P is true, then Q is true. So what this notation means is that if we have a statement, P implies Q, we know this is true, and we also know that P is true, then we can conclude that Q is true. Sounds pretty simple, and it is, but these are axioms. This is what forms the basis. We don't know anything other than these axioms. And that seems like a pretty important and basic thing to know is true. Now you can also write this in our other notation as P and P implies Q, then Q. So if we have P and we have that P implies Q, then we have Q. So these are the axioms of propositional logic. And I think it's worth noting that these axioms are complete. All the things that we can discover must be true according to these axioms can be proven using these axioms. Check out the introduction video to get a better understanding of what complete means. And in that introduction video, I also explain Gödel's incompleteness theorem. And from that theorem, we can say that propositional logic by itself is not enough to describe math. Because it's complete, we know that it's not enough to describe math. Any axiom system that can describe math is not complete. So like I said, there are alternate axiom systems. One of them is called the Łukasiewicz system. In his system, he leaves out the third axiom, the contraposition or the excluded middle axiom, and is actually able to derive that axiom from the first, the second, and modus ponens. There's also the Frege system. In this system, the first and second axioms are the same, but the third axiom, contraposition, is actually reversed. So in that system, the third axiom is this. If P implies Q, then not Q implies not P, which this one is technically called direct contraposition. But what we find in Hilbert's system is that this statement is also true, and this relationship is actually biconditional. That's that if and only if relationship you may have heard of before. Interestingly, Frege's system was the first formal logic to use quantifiers and variables. He also invented first-order logic, and his goal was to reduce math to pure logic, which, looking back, was a success. So it turns out that from these axioms, you can basically derive an additional set of axioms that applies to the connectives that I mentioned. Okay, so the axioms of the connectives, while I might call them axioms, they're more of definitions, which it is a very subtle distinction between those two words, and in many ways they are the same thing. But all of these connectives are things that we defined. They're useful because they represent things that make sense to us, and they're logical. Also, these connectives are defined based on the implication arrow. So in propositional logic, propositions and the implication are the things that we assume. And the axioms that I just talked about define the implication arrow and how propositions and implication work. And so all of the connectives can be defined using just implication. Negation, or not, and it's represented with this weird little bar. So if your statement A is 2 plus 2 equals 4, then not A is 2 plus 2 does not equal 4. In this case, A is true and not A is false. But if A was 2 plus 2 does not equal 4, then not A would be true. And if you think about A as being a circle and everything inside of it, then not A is everything outside the circle forever, or until we put a box on it, in which case not A would be everything inside the box that is not in A. So this not A is also a proposition, but we put that bar on it to denote its relationship to A. Now we can also do something called a truth table. In this case, we're only dealing with one proposition, A, and A, we know, must be either true or false. In this case, not A is false when A is true, and true when A is false. So this truth table shows us the relationship between two different statements. So I'll just call this not one. This one comes from kind of combining the axioms of propositional logic with the law of excluded middle, and specifically representing the law of excluded middle using the notation that propositional logic introduces, which is the version I showed in the previous video. Propositional logic is sort of the first way of representing logic using symbols. It's like the most foundational system of symbols. Now just look at this and realize that these two are not the same thing. Just because one thing implies another thing doesn't mean that other thing implies the first thing. And when you combine these two, you know that A is equivalent to not A. They're actually the same thing. And that sort of makes sense, right? If not A is everything outside of this circle, and first you jump there to not A, and then you take the opposite of that, well, you're just going to jump right back to A. Kind of like, in general, multiplying a negative by a negative, you get a positive. Even in our everyday language, a double negative, we know that two negatives cancel out and give a positive. And then our third and final one just bear with me while I write this. Think about it while I'm writing it. If something is in parentheses, treat it just like math, just like the order of operations. You do whatever's in the parentheses first, and then look outside the parentheses. This arrow is key. What you want to do is compare what's on the left side, what I just wrote, with what's on the right side. So if A implies B, then if A implies not B, then not A. So assume that if A is true, B must be true. Then if A implies not B, so assume that A implies not B is also true, so that we can see what the arrow tells us is next, then not A. So if A implies B and A implies not B, then we must have not A. But at the beginning we assumed A, right here. In assuming that A implies B, we're also assuming A, that A is true. So if we assume that A is true, and we have that A implies something called B, and we also have that A implies some other thing that happens to actually be the exact opposite of B, then we can conclude that A is false. Now, if you've taken even an introductory math class at the college level, this might be starting to sound familiar. This is really proof by contradiction. It's saying that if we assume A is true, and then we find that B is true, but we also find that B is false, then we can conclude that A was actually false. So we don't have to prove whatever not A is. We can just prove that its opposite implies a contradiction. Okay, so our first actual connective is called disjunction. Disjunction is basically just or. When you see it written, think or. And it's written like this in the notation of propositional logic. So A or B is defined using only the implication arrow and negation as not A implies B. So if you want A or B to be true, then if A is false, B must be true, and the other way around. That is to say, at least one of them, A or B, has to be true in order for this whole thing to be true. So if you do not have A, then you must have B. But you could also equally say this. If you do not have B, then you must have A. Now this definition isn't really useful, but I show it to you just to show how the connectives can actually be defined using only propositions and implication. Because the axioms of propositional logic that I've already showed you only describe how implication works between propositions. So that means that anything additional that we define, like this thing that we call disjunction, has to be rooted in those axioms. So right here, we've written a statement which is equivalent to this, but we've used nothing more than the implication arrow. And again, yes, we did use this negation, but that is part of the proposition. What does it mean for two statements to be equivalent? It means that they have the same truth values. So let me show you what that looks like. So we have our truth table, and we have to consider all possibilities of A and B. So we could have that both are true. We could have that one is true and the other is false. And we could have that both are false. That's all possibilities. So what are the truth values of this statement, A or B, for each of these possibilities? Well, if A and B are both true, then the statement A or B is true. Because if A and B are both true, then you do have that A or B is true. And how about for one being true and the other being false? Then A or B is true. And the same thing for this one. If you have one of them, then you do have this one or that one. If you have neither A nor B, then you do not have A or B. These are our truth values for A or B. Now, the truth values for this. So for this first possibility where they're both true, if A is true, then not A is false. So we have false implies, and B is true. So we have false implies true. Well, the way this implication arrow works is it just says, if this thing is true, then this thing is true. But what if this thing is false? Then the implication arrow doesn't tell us anything about what comes next. So if the first thing is false, the whole statement, this implies that, is true. Whether a false thing implies a true thing, or a false thing implies a false thing, both of those are considered true because either one of them could be true. So this one is true. Now we're going to have the same thing in this second one because A is true, so not A is false and B is false. So a false thing implies a false thing. Now in this one, A is false, so not A is true, and it implies B, which in this case is true, and that's going to be true. And for the last one, you've probably caught on by now. Not A is true, B is false. So if the first thing is true and the second thing is false, we have not A implies B is false. So this one is false. And we can see that these two statements are equivalent because they give the exact same truth values. Within this system, these truth values are really the only way we have to sort of measure these abstract sort of objects that we're working with, these propositions, the way that we're relating them to each other. So there is no other information that we could get, that we could gather from these two statements. The only thing we can possibly know are these four truth values, and we find that they're the same, so there's no way for us to distinguish between these two statements, and therefore they're equivalent. So if you think of A, again, as everything inside this circle, and B as everything inside this circle, then A or B means you're inside one of these circles at least. Maybe you're in both, this center area, but you're at least in one of them. So this entire space is A or B. Okay, let me show you our axioms or our definitions. The first one is A implies A or B. So if A is true, then we can safely say that A or B is true, regardless of what B is. And the other one, B implies A or B. The third one, if A implies C, then if B implies C, then A or B implies C. So if we assume that A implies C, then we know that this must be true. So what is this? This says that if B implies C, then this must be true. So in order for this to be true, we must have that A implies C and that B implies C. Then this says if A implies C and B implies C, then if you know that either A or B independently is true, then you can conclude that C is true. And it's a very confusing way of saying something that is very obvious. So you can think about it like this. If you have A implies C, then A is like a circle that's inside of a bigger circle called C. If you're inside A, you're definitely inside C. You know that for sure. Okay, and we also know that B implies C. So if you're in B, you're definitely in C. Because if you think about this the other way around, if B was out here, C was inside, then if you were in B, you could be out here. You cannot conclude that you're in C. So these are the two things we know. Now, if you have A or you have B, so if you're in here or you're in here, then you're in C. And now that we know that, we can kind of draw a more complete picture. So you could be anywhere inside here. You could be in A, you could be in B, or you could be in A and B. Then you must be inside C. So that's disjunction. Okay, now let's move on to conjunction. Conjunction is basically and it's represented with this wedge, which is pointing the opposite direction from disjunction. I remember it because this looks like an A for and. So this one can be represented using nothing more than the implication arrow and negation. And notice the similarity or the symmetry between the definition for conjunction and disjunction. And this one is disjunction. It's almost like the negation gets distributed, but of course this isn't actually distribution because these two statements are not equivalent, as you'll see when we make the truth table for this statement. The first part of the definition for conjunction is, so if A and B is true, then A is true. The second part is, if A and B is true, then B is true. So together they say, if this whole statement A and B is true, then individually A is true and B is true. Now this might sound really simple, but it's really important to drill into your brain because these are our starting assumptions. These are the only things that we assume at the beginning, and then you can spend years studying propositional logic, and all of that stuff that you learn is a logical consequence of nothing more than this. The third definition is A implies B implies A and B. If A is true, then if B is true, then A and B is true. And altogether, this really just says that if A is true and B is true individually, then the whole statement A and B is true. This one goes in the opposite direction from the first two. Now, if you look at our definitions for disjunction, the first two sort of form this little pair, and then the last one goes in the opposite direction. But in disjunction, the first two deal with the individuals implying the whole statement, while in conjunction, the first two deal with the whole statement implying the individuals. And again, the last one sort of stands alone and goes in the opposite direction from the first two. And I just find that to be a cool little symmetry. Now let's do the same thing for conjunction. If A is this circle and B is this circle, then A and B is in here. You have to have both. Now, if you'll kind of compare these two illustrations, just kind of look at them for a minute, see if you notice anything. One thing I noticed is that they have some overlap. See how they both fill in this central region? The overlap between these two pictures is that they both fill in the overlap of A and B. And I thought that was kind of interesting. So what do and or have in common? Well, they have and in common. Now let's make our little truth table. We can have both true, one true and the other false, and both false. So if A and B are true, then A and B is true. If even one of them is false, then A and B is false. And of course, if they're both false, then you do not have A and B. Also with this, notice the symmetry between these truth values, 3 trues and a false, 1 true and 3 false. And I'll leave it to you to figure this one out and verify that it matches these. But first, let's have a look at implication itself. So implication is technically a connective. It connects propositions and tells you the relationship between them. The definitions of implication are just the axioms of propositional logic, so I won't write them again here. But let's look at the truth table. So if A is true and B is true, then A implies B is true. If A is true but B is false, then A implies B is false. It's like if you have this statement, A implies B, and you want to know if it is true, and then you find that A is true but B is false, then A implies B can't be true, because what you have is a situation where you do have A but you don't have B. So it cannot be the case that A implies B. However, if A is false, then it doesn't matter what B is, because you want to know if A implies B. Well, if your situation is that A is false, then that doesn't tell you anything about B. That puts no restrictions on what B can be. So anytime A is false, A implies B is true. So you can think about this as you have a circle, which is B, and inside of it is A. So think about this first one. A is true, so we're inside A, and B is true. Well, if we're inside A here, we're clearly inside B. So A is true and B is true. However, if you look at the next one, again, A is true, so we are inside of A, but B is false. Is it possible to be in A but not be in B? No, it's not. And that's why the statement as a whole is false, because this setup with A inside of B is how we represent A implies B. And in this configuration, we cannot have a situation where A is true and B is false. Back here in something like disjunction, we could have that A is true and B is false and have the whole statement be true, because this is how we represent disjunction, not with one inside the other, but with the two circles overlapping. Now in this next one, A is false, so we are somewhere out here, anywhere but A, and B is true. So that limits us now to everything that is B, which is not A. And in this last one, they're both false, and I think you can figure out that that would represent being anywhere but A or B. Finally, our last one is the biconditional. In set theory, the biconditional basically becomes the equal sign, but it says if and only if. So A biconditional B is saying that if A is true, then B is true, and if B is true, then A is true. This means you can't have one without the other. And no matter how you think about this, whether it's as overlapping circles or a circle within another circle, you will always have the possibility of having one without the other. So these could not represent the biconditional. What this biconditional is saying is that we have A and we have B. They are exactly overlapping, taking up exactly the same space, because if we have even just a little bit that's coming off, if you were in here, you could have B but not A, in which case it would not be true that if you're in B, then you're in A. The only way that this is true in both directions is if the circles perfectly overlap, and essentially A is equal to B. Because no matter what statement you can come up with that ends with implies A or implies B, just that conclusion of finding one of them, you automatically can conclude that the other one is true also. If you have this, if you know that this is true. And remember that A implies B is like this, then B implies A would be like this. The only way that you can have A inside of B and B inside of A at the same time is if they are exactly the same. So I'll just write these out quickly, because at this point I think you're probably starting to see the pattern. I'll just write out these definitions quickly, because once you see them, I think you'll start picking up on the pattern. So if A implies B and B implies A, then A implies B. Now just remember that these are just symbols, and we are defining these symbols. So we're defining this symbol, because when I say it in words, it sounds kind of funny, because the words are representing these symbols, and these symbols are what allows us to discover and express these very complex logical or mathematical ideas. It's a way to write down on paper what we are thinking, because we couldn't possibly hold all of those equations, calculations in our heads. We have to write them down, but the symbols have to be very precisely defined in order for them to be logically consistent and allow us to do these many, many steps of manipulation of equations and statements and have the end result actually be logical and useful and still make sense. So this A biconditional B implies that B implies A. So if you know this, then you know that this is true. And the same for the other way. And the third one is if A implies B, then if B implies A, then we know that A biconditional B. So if we know both of these, then we know this. Again, the third one going in the opposite direction from the first two, which form a pair. And our truth table, so if they are both true, then this whole thing is true. if they are both false, then it is also true, because if they're both false, then neither one of them puts any restrictions on the other. But if A is true and B is false, we know from the previous one that the A implies B part of this is false. So, of course, the whole thing must be false. But now this situation is just the reverse of that, and turns out that this whole statement includes the reverse of that. It includes that B implies A. So this one is false as well. So I have one more topic I'd like to cover before the end of this video, and that is DeMorgan's laws. These laws tell us how negation interacts with conjunction and disjunction. For conjunction, the rule is that not A and B is the same as not A or not B. Because if you do not have A and B, that means at the very least that you either don't have A or you don't have B. Possibly you don't have either. And for the other one, not A or B, we have not A and not B. Because if you do not have A or B, if A or B is false, the only way that you can have that is if you don't have either of them. And we can look at a truth table. So if A and B are true, then A and B is true, but then not. So you flip it, and it's false. If A is true and B is false, then A and B is false, but then you flip it and make it true. And the same goes for the others. In both of these, A and B is false, then negation makes it true. Now look at this one. If A and B are true, then not A is false and not B is false. And we have an or. If both things are false on either side of a disjunction, then the overall thing is false. If A is true and B is false, then not A is false and not B is true. One of them is true, so the overall disjunction here is true. And the same for the others. Now the exact same reasoning follows for this one, giving us true. And if A and B are false, then both of these are true and the overall disjunction is true. And we can see that the two are equivalent. Now I challenge you to do the same for this one. Now remember the law of non-contradiction. I represented it like this: not A and not A, saying you cannot simultaneously have A and not A, or rather A being true and false. And notice how this looks a lot like this. Then recall the law of excluded middle, which I wrote like this. So according to this law right here, these two statements are equivalent. Do you see how this is the same as this, and this one is the same as this one? It's just that we've replaced B with not A. Take a moment to look at that when you replace B with not A, how you end up with this and this. So all we've done is sort of distributed this negation using DeMorgan's laws and gotten this, which shows us that the law of non-contradiction and the law of excluded middle in propositional logic, which is a part of classical logic, are equivalent. Okay, this pretty much brings us to the end of what I wanted to share with you about propositional logic. I do have one thing that I want to mention, and that is the connection between propositional logic and set theory. So it turns out that propositional logic and set theory are isomorphic. So I used this little symbol that looks like an equal sign, but it's not, because propositional logic and set theory are not literally the same thing, but they are isomorphic, which is what this symbol means. That means that everything that is in propositional logic has an equivalent in set theory. All of the objects used in either theory can be mapped one for one onto each other. And to give you an idea of what I mean by that, there's a reason why I have been representing some of these connectives using circles. So if you'll recall, conjunction I represented as two overlapping circles where we're trying to represent A and B. And I said that A and B was this region where the circles overlap, because both propositions A and B are true in that overlapping region. In set theory, we have something called intersection. So A intersection B. And this picture here is actually representing this intersection in set theory, more so than this conjunction, connective, in propositional logic. But the two concepts are logically and conceptually the same. We also had disjunction, which was basically the combination of A and B. So if you have A or B, then as long as you have one of them, you're good. Well, in set theory, we have union. And again, this picture here really represents A union B. Also, we had negation. So if we wanted to represent not A, then we have this circle A. What do you think not A would be? If A is everything in the circle, then not A is everything that is not in the circle. And in set theory, if we have a set A, then our not A is called the complement of A, and it's represented like that, with a little c in the superscript. Okay, and our implication arrow, which we represented like a circle inside a circle. So this would be A implies B, because if we have A, then we certainly have B. Well, what does this look like? We have a circle completely contained inside of another circle. In set theory, this is called the subset. And there's two kinds of subsets, a proper subset and then just a regular subset. I'll talk about that in the video on set theory. But if we ever see A is a subset of B, that's just saying that A is completely contained inside B. All of the elements that A contains are also contained in B. Now, this concept of elements in a set is fundamental to set theory. There's no point in having set theory, and you couldn't have set theory if you couldn't talk about the elements that are in the sets. What do these sets contain? But the next video on first order logic is going to introduce the concept of elements in a set. Propositional logic doesn't have the tools to talk about individual things for which a proposition is true. It really only talks about whether a proposition is true or false. But first order logic introduces something called predicates, which allow you to represent logically propositions which are true for some things but not for other things. And finally, the biconditional, which was just two circles which are perfectly overlapping with each other. And in set theory, this becomes the equals sign. So A is equal to B. So I'll come back to all this in the next video, and again in the video after that, and then it will sort of culminate and we'll see the consequences of this connection in the next video after that, which is going to be set theory. So thank you so much for watching. I hope you found this interesting. Some real mathematicians might take issue with some of the things that I've said, and there are two main reasons for that. One is that I'm not a mathematician, and I've also not studied pure logic very deeply, so I'm sure there's subtleties here and there that I don't even know about. However, I try to only present information that I do know about. And the second reason is that I tried to kind of simplify all this stuff without oversimplifying. I'm trying to present this information in a way that hopefully almost anyone could understand, but at the very least, I want someone who has not taken classes on these topics to be able to understand some of the basics and start to see some of the patterns. I'm also trying to present the very first and most basic information that I think a person should know before studying these particular topics further. I like to introduce people to interesting things that then inspires them to go and research those things more. So anyway, I hope you found this interesting. I hope I have inspired you to look into propositional logic, and I hope I've helped you see some of the patterns that exist in this most foundational and fundamental field of logic. Please consider subscribing, maybe even clicking on the notification bell so that you can get alerted when I make my next video. Drop a like if you feel that I've explained these topics in a way that made sense to you. And please comment if you have any questions, if there's anything I didn't quite explain well enough, if there's any future topics you'd like to see a video on, anything like that. So, thanks for watching.